Hi everyone. So our second speaker is Rachel, who is in her final few months of her PhD with the University of Exeter and is based at British Antarctic Survey in Cambridge. And her PhD work involves looking at high resolution measurements of chorus waves to investigate their impact upon the radiation belts. So I'll let you take it away. Thanks.
Perfect, thank you. Today I'm going to be talking about the variability of chorus wave power on short timescales in the radiation belts, but particularly I'll be comparing sort of low resolution averaged wave data that is typically fed into belt models to much higher resolution wave measurements. They're averaged more on the timescales associated with small scale wave particle interactions and wave-wave interactions. So just to first set the scene, what are the radiation belts? The radiation belts are an energetic particle population that are trapped in Earth's magnetic field. And you can see in this plot here on that, let me just put my uh, thing on. Here we go. Can you see my pointer?
Yeah, I can see the point.
Okay, perfect. Um, The electron radiation belt is the lowest density and highest energy population of all of the plasma populations in the magnetosphere. And if we play this movie, you can see that the um, particle flux is represented here by the different colors of the radiation belts in this slice through the donut region of the radiation belts, sort of demonstrating how variable and dynamic this population is. And these dynamics are primarily driven by injection of particles into the inner magnetosphere during substorms or enhanced convection. Now, with these dynamic particle populations in the inner magnetosphere comes plasma instabilities, which generate waves. So in this diagram here, I have a sort of very basic representation of the different wave modes that can exist within the magnetosphere. But the wave mode that we're most concerned with in terms of radiation belt dynamics today is Whistler mode chorus, which is a wave mode that is generated due to temperature instabilities when we have those particle injections into the inner magnetosphere. And as the electrons drift around eastwards, they generate these Whistler mode chorus waves. They have a frequency between the lower hybrid resonance and zero point 0.9 of the gyro frequency. They also, as you can see from this pink blob, exist outside of the plasmasphere due to the density conditions. Typically, also, if we look at their power spectral density, they have a characteristic upper and lower band, separated usually by a gap here at half the gyro frequency. Now, why are we concerned with these waves in particular? So here I've got a very simplistic view of the inner magnetosphere, and chorus waves can undergo resonant interactions with these energetic particles in the radiation belts. So here I have an example of a red particle there spiraling around its field line, where if it meets a wave with a Doppler shifted frequency that matches the gyro frequency around this field line, we can get a resonant interaction and exchange of energy as described by this resonance condition. Now, obviously, this is just one interaction, and the radiation belts are a global phenomenon. So, how do we model what's going on a larger scale? We tend to use a quasi-linear diffusion theory to describe the entire particle population in terms of, for example, their pitch angle and energy, and a slow diffusion across these coordinates over long time scales in the particle phase space. So here is a very complicated, scary looking equation describing this quasi-linear diffusion. But I want you to focus on is the diffusion coefficients circled here, which are essentially the a set part of the equation in which all of the physics describing these wave particle interactions are fed into. So to do so, we have to begin with wave observations to create empirical wave models describing the important wave parameters required to then calculate these diffusion coefficients. These are then popped into the diffusion model, which provides out particle fluxes, which we can then compare with observations of the particles. Now, in the stages of this pipeline, I'm going to be focusing on the wave observations in particular today. And returning back to this idea of quasi-linear diffusion, in this framework, to build up that picture of a diffusive random walk of the particles across pitch angle and energy space, we have to have sort of small um, tiny little kicks of the waves upon the particles, so that we're just getting this building up this random walk, and that requires a few conditions upon the waves. Firstly, they must be small amplitude in comparison to the background magnetic field, such that they are just small perturbations for this linear equation. They also must be slowly varying with time, such that we essentially have a stationary wave spectrum whilst the particle distribution is evolving. So there is very, very weak feedback of the particles on the waves in this picture. It's just the particles evolving according to a stationary or quasi-stationary wave spectrum. This means they have to have no growth or damping, or very, very small growth or damping rates associated with the waves. They must also be sort of related, incoherent, and broadband waves. So essentially, we can't have coherent waves such that particles can get trapped in a particular wave mode or experience multiple interactions with a particular wave mode such that their interactions become deterministic. And that's the sort of key word here. For this quasi-linear diffusion picture, particles must evolve stochastically in that random walk manner, not deterministically. So just to do a brief description of what can occur if we instead have waves that do not fulfill these linear diffusion criteria, there are various particle responses as a result of nonlinear wave-particle interactions. And here I'm going to demonstrate this with 3 examples from test particle simulations that were published in 2008 by Jacob Bortnick. And in these test particle simulations, each start with 24 particles that have initial phases spread uniformly between 0 and 2 pi. For the first test particle simulation, we have quasi-linear friendly waves. We have low amplitude, broadband, negligible growth rate waves. The resonance condition occurs here. We have the waves interacting with these 24 particles at this point, and you can see that this spread in pitch angle is sort of uniform across a very small range due to this initial random uniform spread between 0 and 2 pi of the particle phases. However, if we were instead to increase the wave amplitude by a factor of 10 in this test particle simulation, you can see that we have a much larger jump in pitch angle and energy. And as well as this, the phases have sort of all bunched together. This response is known as phase bunching. Another nonlinear response that we can see if we increase the wave amplitude and also change the location of the particle resonance is phase trapping, where this particle coloured in red, has been essentially trapped in the wave potential and accelerated and scattered much, much larger pitch angle and energy ranges. So you can imagine that B and C, these 2 particle responses, don't fit with that vision of slow diffusion across pitch angle and energy space. So the aim of my study was to focus on when and where waves that are potentially unsuitable from the point of view of quasi-linear theory may be. And to do so, we use measurements from the Van Allen probe's spacecraft, which were a twin pair of spacecrafts that were orbiting in and out of the radiation belts between the years of 2012 and 2019. They had highly elliptical orbits, and on board the spacecrafts were the emphasis instruments, which provided 3D electric and magnetic wave field measurements throughout the radiation belts. Now, returning back to my simplified picture of the inner magnetosphere, adding in my satellite, the emphasis instrument took measurements of the waves 35,000 times a second. So here we have an example of this waveform amplitude with time. However, they couldn't possibly send down every single raw waveform that was measured due to telemetry limitations on what the spacecraft could send. So therefore, they have a survey mode where they provide snapshots of the wave data by performing Fourier transforms on sections of the raw waveforms every 6 seconds. Now, this is quite an ugly representation of the survey data here, and this is because I'm trying to show that whilst we received the survey mode every 6 seconds, it was actually just a Fourier transform over the first half second of that period, followed by a lot of thrown away data and then another half second Fourier transform. So therefore there are large they're just snapshots of what the spacecraft is seeing. Just to describe that a bit more clearly here, I've got an example of two 6 second time periods of the raw waveform. The green shaded area of this waveform is the section of the measurements upon which the Fourier transform was performed to provide a power with frequency, spectral density at every 6 second timestamp. And additionally, this was also rebinned into a semi-logarithmic frequency range to further allow storage to be reduced. Now, the Van Allen probes also had a burst mode, which triggered sometimes to provide the full set of 3D waveforms for a given 6 second sample on some occasions. So we didn't always have this, but sometimes when the burst mode was triggered, we also had the corresponding 6 second raw waveforms to a given survey time period. So when we have this, we can perform multiple FFTs upon the raw waveform, so we can improve the temporal resolution of the sample we get. And you can see here, this is pulling out the structure of the wave far better than this survey snapshot is. So just returning to back to that idea of a perfect chorus wave in terms of quasi-linear theory, here I have two burst record examples that contain chorus waves. And in this first one, we have an upper band and a lower band. However, they're relatively broadband. There's not much structure going on within this chorus wave. Whilst in the second example, we again have a lower and upper band, but the lower band has these rising tones, and they're changing with frequency. And the upper band is also far more transient. Now, before we move on to investigating these wave spectra, let's define an indicative nonlinear power threshold. So this is the power at which we expect a wave-particle interaction to become nonlinear. And this occurs when the force of the wave upon the particle at resonance is much larger than the background field mirror force upon the wave. And we can use that to define this threshold to where we might expect to switch over from a quasi-linear friendly to a nonlinear interaction. Now, this depends on lots of the wave background field and particle parameters, but for our study, we assume that the interaction is occurring between relativistic electrons with near parallel chorus waves. And all of our chorus waves were at equatorial latitudes and in the heart of the radiation belts. So we're returning back to our two examples now. They have been integrated between this chorus frequency range, between the lower hybrid and 0.9 of the gyro frequency. I've also listed these assumptions again for quasi-linear theory, that we must have small wave amplitudes, we must have slowly varying waves, and we must have incoherent broadband waves. You can see in example 1 that the integrated power never crosses this non-linear threshold until the end here. So we've essentially fulfilled assumption A. The power is very slowly varying. There's not large differences with time. Fulfilled assumption B. And as we saw in the spectra, they were relatively broadband waves. However, in example 2, you can see that where the location of the rising tones we're consistently going orders of magnitude above this nonlinear threshold, and there's significant variation within the power. And again, from the spectra, we know that we don't have broadband waves given those rising tones. We wouldn't have been able to see this had we not had the burst mode data. So to investigate the sub-second chorus wave power across all of our Van Allen probe measurements, our first steps was to identify all of the chorus waves in the survey dataset and check if there was a corresponding burst sample that existed. Doing this, we found over 700,000 chorus containing records. Following on from this, we wanted to parameterize the chorus power and the power variability by geomagnetic parameters. So firstly, we separated our power into the separate frequency bands, the chorus frequency bands, and defined a variability statistic. So here again, we have an example of a burst mode record of a chorus wave, where we have the low frequency between the lower hybrid and 0.1 of the gyro frequency, the lower band between 0.1 and 0.5 of the gyro frequency, and the upper band between 0.5 and 0.9. And so these frequency bands are all integrated with frequency separately and treated apart in our statistics. Our statistic of variability is something called the normalized interquartile range. And this is essentially for each integrated power, the difference between the 75th percentile and the 25th percentile, all divided by the median to provide a sort of normalized measure of the spread of the power for a given frequency band for a given burst sample. So to sort of explain what this looks like in terms of our spectra, I have three cases. This first case here, we have again our nice broadband lower and upper band waves, and the IQR for these stays around 1. If instead we have rising tone elements here in the lower band, however, they're significantly overlapping in temporal space, our normalized interquartile range rises to 4 for this lower band, whilst the upper and low frequency bands remain around 1. Now, again, we have another example of lower band with rising tone elements. However, there's distinct separation between some of these elements such that they're not overlapping at all. And you can see that this means that their normalized interquartile range rises up to 10, whilst the others remain around 1 again. So essentially, we're using this sort of measure of the spread of power as indicative of how structured the wave spectra are. Moving on to the global statistics now of our chorus waves. We're binning these by their frequency band and L star and MLT. So if we first look at the power in the survey and the maximum power in the burst for our low frequency, lower band, and upper band waves, you can see that the lower band have much higher average powers compared to the other two frequency bands. And we also investigated these variability statistics. So if you just ignore this power ratio in the third row here, today we're considering this normalized interquartile range. Now, there's a lot of different features we could identify in these plots here, but for the sake of time, I'm just going to focus on these lower band statistics. We did identify lower band in over 75% of all the chorus waves identified. And additionally, they have the highest powers. So now that we have separated all of our chorus waves into their respective frequency band and defined the variability, we want to investigate what the effect of two different parameters are upon these chorus wave statistics. So firstly, geomagnetic activity by using the AE index and the ratio of the plasma to the gyro frequency. So first here, I'm showing the maximum power in the burst averaged in these MLT and L star bins, but this time separated by activity levels. So we're going, as we go across this row, we're going up in activity, starting from quiet through to moderate active conditions. Again, you can see there's a clear increase in the average power within particularly this post-midnight morning sectors as we go up in activity. And if we plot the probability distributions of these powers, the quiet powers are plotted in blue, the moderate in yellow, and the active conditions in red. You can see that the active conditions sort of have this double peaked probability with low power and high power waves. And overplotted on top of these with this dashed vertical line is the nonlinear threshold. And you can see that the second peak for these active conditions is beyond this nonlinear threshold. And in fact, over 25% of our chorus waves identified within active conditions had maximum powers beyond this threshold. If we then move to the variability statistic, separated by activity level, you can also see an increase in the variability as we go up in activity from left to right. And again, there's sort of a double peaked situation in which we have low variability waves below that value of 1, describing that broadband structure, and a sort of heavier tail of these higher variability waves. And growth of this tail occurs as we go up in activity. If we now do the same, take the same two statistics but separate them by the ratio of plasma to gyro frequency, we see the opposite relationship as we go down in the ratio, we see larger average powers. And again, these largest average powers are focused within this low FP over FC ratio, and essentially all of the chorus waves that exceed our nonlinear threshold are within these conditions. And finally, if we group the normalized interquartile range by this ratio, we also see this negative correlation between the ratio and the variability of our waves. And actually, before we did see these double peak distributions when separated with activity, if we instead do the separation with this ratio, you can see that we're basically completely isolating these low variability and high variability waves. So this is essentially telling us that the majority of our structured chorus waves are occurring when the plasma to gyro frequency ratio is below 5. Finally, to further distinguish between our populations and separate the importance of geomagnetic activity and the plasma to gyro frequency ratio, we created these statistics where we averaged the power and variability into activity and ratio quantile bins. So first, if we consider the power in the survey and the power in the burst here on the left, it seems that our highest power waves are most associated with high activity across all of our X FP over FC bins here for both the survey and the burst data set. So as you go up each column, you can see an increase in the average power. So it appears that the activity is really controlling these increases. However, if we then look at our variability statistics, particularly focusing on the normalized interquartile range, we see almost the opposite, that our highest variability waves are almost entirely controlled by this ratio, that as we go along the row, this value of the variability decreases for each activity level. So this suggests that whilst the power of the chorus wave is being controlled by the activity level, the variability of this chorus wave is actually more highly associated with the plasma conditions in which the chorus wave has been observed. So just to summarise these results, we have investigated sub-second chorus wave power in different frequency bands using emphasis burst mode data, and today I only focused on results for the lower band power, for which we observed the largest powers during active conditions according to the AE index, whilst the power variability peaked at low ratios of that plasma to gyro frequency for all activities. The lower band waves also exceeded the nonlinear threshold in over 25% of measurements during active periods. So our sort of conclusions from this are that the ratio may have an important role in controlling these sub-second chorus wave variability as opposed to the power. And it would be also really interesting to perform test particle simulations on how these realistic power spectral densities of the chorus waves may affect our knowledge of nonlinear interactions. So I'll just leave it there.